Hello everybody, in this lecture we will be solving 1999 IMO problem number 6. Here is a view of this problem. We would like to find all functions defined from in real numbers and mapping onto the real numbers such that the following functional equation is satisfied for all real numbers x and y. So let's assume that f is such a function that satisfies this condition, and let's first try to establish the value f of 0. For now, let's just denote it as c. Now if I plug in x equals y equals 0 into the function equation, I would get f of 0 minus f of 0 equals f of 0 plus, 0 times f of 0 will vanish, so next term would be plus f of 0 minus 1. We decided to call f of 0 as c, so this would imply that f of negative c is equal to f of c, the inside, plus c minus 1. Now I would like to point out that this implies c cannot be equal to 0. Because if it were equal to 0, then these two terms would have cancelled out and c would have to be equal to 1, but that's a contradiction because we assumed then c would be 0. So therefore c is non-zero. So f of 0 is not equal to 0. And now consider the following. Let's assume, so we know that f maps all real numbers onto the set R, into the set R. Let's assume that the range of this is, so the function f will take the set R and it will map it onto W, which is a subset of R. Okay, so W being a subset of R. So this is the range of our function. So so let W be in W, which is basically the range of f, right? F of R, and so if we replace f of y here with W, and W here, and W here, and I'm also planning to replace x with say z, so just for notation sake. So therefore what will happen is that, so we decided that we will replace f of y with W, and we would also replace x with z. So if we make these, if we plug in these numbers into the function form, we would get f of z minus, recall f of y was w, is equal to f of w plus zw plus w, f of x, sorry, f of z I should say, sorry for that. This is just f of z minus 1. Now here I should be careful on what I say here. Z is still in R, because but W is in little w is on capital W, which is a subset of R. It's on the range of our function. So when this is the case, now I can make the following trick. If I further take Z as W, if I set z is equal to w, namely that I also make this, I take the number z from the set w as well, what I get is that f of w minus w is equal to f of w plus w squared plus f of w minus 1. And so this is f of 0 basically, but we realized f of 0 was just equal to c, which is a non-zero. So this would imply that f of w is equal to, so c minus w squared plus 1, c plus 1 minus w squared, all divided by 2 because we have two f functions, for w in W, which is a subset of R. So therefore we have a candidate for the functional form of f. Now the critical move would be how to expand this formula for all the real numbers, because the domain is the whole set of real numbers, not a subset of it, right? A subset W of that whole set. So can we expand this function so that it applies to the whole set R? Now the trick is that I claim, and I need to prove this claim obviously, that every x in R, every real number x in R can be written as a difference of two numbers from W, right? Of W minus W1 from as a difference let's write it like this: W1 minus W2, where W1 and W2 are in W. Recall W is the range of our function. So this claim, if I can prove this claim, then I would be able to extend this closed form function onto the whole real set, and that's my objective. So let's start by the following. So for W is equal to C, remember C is equal to f of 0. Yeah, so if I replace W with C in our functional equation, namely this one, see what we get. So we have f of z minus c. By the way, remember here that z was any real numbers, so that's good. Is equal to f of c plus z times c plus f of z minus 1. But then if I move this f of z to the left hand side, I would get that this would imply f of z minus c minus f of z is simply equal to f of c plus z times c minus 1, and this is true for z in R, for real numbers. Now finally, in order to achieve the desired result and complete the proof, I just observe that if I replace here z with the following: z is equal to x plus 1 minus f of c over c. Remember that c is non-zero. So what will happen here is that the c's will cancel out, and then the plus 1 and the minus 1, and f of c's will cancel out. And so the right hand side would, so this would imply that, this careful choice of the variable z would reduce the right hand side here. Let me actually use a different color. So it would reduce the whole thing into x, but then I can just rename these two guys as u and v, and as a result x itself becomes the difference u minus v, where both u and v are on the range of our function. So that's really nice. So therefore x is equal to u minus v for uv in I think we called it as w. So therefore now I can go back to this equation one more time, and in this equation, if I make use of so if I make use of this equation, plugging in z is equal to u and w is equal to v, z is equal to u, w equal to v, w is equal to v, z is equal to u. So I have the following: so f of u minus v, so I would get, so therefore f of u minus v, recall that this was just x, so this is simply f of x altogether. So the whole thing is okay, so the whole thing is equal to f of x. Let's just write that down, I guess. F of x would simply be equal to, having replaced w with a v, we would get f of v minus uv, sorry, plus uv, plus f of u minus 1. So this is f of v plus uv plus f of u minus 1. That's a v plus f of u minus 1. And now I can apply the definition of f that I found out earlier here, namely this one, and this definition works for any w in W. So therefore both v and u are from W, so therefore this would imply that replacing it with v first, that's a v, c plus 1 minus v squared over c over 2, I think. Was it c or 2? Oh yeah, it's 2. It's a 2 here. So therefore dividing it by 2 plus uv plus, again the same thing, c plus 1 minus u squared over 2 minus 1, and this simply will give us, so we can add these two results. I would get c plus 1 on this one, and then a minus 1, so there's a c remaining, so c plus uv minus, so therefore we would get c plus uv minus u squared plus v squared all over 2. But then this is just 2uv over 2, so therefore this would become c minus u minus v over c minus v squared all over 2. But then u minus v, recall, was equal to x, so that's just c minus x squared over 2. So that's f of x, right? So we established this was f of x. Wow, so this is equal to 4x in R. But finally, if you compare this formula with the earlier formula, they have to agree, right? Because W is a subset of R, so therefore making them agree to each other, right? So we get that. So let's make them equal to each other. So for instance, in this equation, I can plug in W. It should still work. So f of W is equal to c minus W squared over 2. But then plugging in W here is c plus 1 minus W squared, c plus 1 minus W squared over 2. So I can just write this as 2c all over 2. There's a minus sign in between. Let's just organize it like this. So the 2's will cancel out. So I would get, and the minus W squares will cancel out. 2c is equal to c plus 1. Finally, we get that c is simply equal to 1. And now, finally, our functional form is therefore equal to, so in closed form, this is equal to 1 minus x squared over 2. Now, all that remains is to verify that this indeed satisfies the functional equation. But obviously, this is not too hard, and I leave it to you guys as a homework to verify this result. So, hope you enjoyed this video, and looking forward to see you guys in our next lecture.